72 hours sounds like a countdown to impact. It sounds like a warning. It sounds like something big is about to happen to Earth. But with 3i Atlas, the reality is stranger and calmer. At the same time, the countdown is not to collision, and the systems that begin to fail are not city lights or power grids. The systems that strain first are the ones we built to measure the sky telescope's tracking software orbit models, prediction pipelines, because in the last 3 days before a fast-moving visitor reaches a key point in its trajectory, the sky becomes a more difficult place to do precision. 3i Atlas is the third confirmed interstellar object ever found passing through our solar system, discovered by the NASA-funded Atlas survey and reported on July 1st, 2025. It is unbound to the Sun, arriving on a hyperbolic path and leaving the same way, which means it is not one of ours. It already made its closest pass to the Sun in late October 2025, about 1.4 astronomical units just inside Mars' orbit. And it already made its closest approach to Earth in mid-December 2025, still far away, about 1.8 astronomical units, roughly 270 million kilometers, never a threat. So what is the countdown to now? It is a countdown to a moment when its path takes it into a geometry that makes our work harder and makes its behavior easier to misread. In mid-March 2026, 3i Atlas passes relatively near Jupiter at about 0.358 astronomical units, tens of millions of miles away. That is still not a collision. That is not even a close pass in the everyday sense. But Jupiter is massive, and the space near it is crowded with gravitational effects, resonances, and changing viewing angles. For an interstellar object that is already moving fast, a Jupiter encounter is a moment when ephemeris predictions can tighten dramatically or wobble, depending on how well we measure it in the days immediately before and after. And here is the part that makes headlines erupt. 3i Atlas is not a silent rock. It is a comet active venting gas and dust. NASA notes that when it was discovered, it was moving about 221,000 kilometers per hour, speeding up to about 246,000 kilometers per hour near perihelion, then leaving the solar system at essentially the same speed it arrived with. It shows a coma and tails, including rare-looking structures, and scientists have reported wobbling jets tied to its rotation, with a rotation period around the scale of about 15 hours. That activity is the quiet engine behind the change course stories. Outgassing acts like tiny thrusters. If gas escapes more strongly from one side than the other, the comet gets a small recoil push. That push is not science fiction. It is one of the oldest, most familiar complications in comet orbit fitting. But for an interstellar comet, those tiny pushes are more dramatic in our models, because the object is fast, the observing window is limited, and the geometry shifts quickly. In the final 72 hours leading into a key observing moment, small mismatches between a gravity-only prediction and the sky's actual data can grow more visible, not because the comet is steering, but because our assumptions are being tested by a moving, venting, rotating body. So tonight, the story is not that a cosmic intruder is approaching Earth and breaking civilization. The story is that a rare visitor is approaching a measurement bottleneck, a stretch of time where a few things happen. At once, the comet's apparent motion accelerates across crowded star fields. The viewing angle changes rapidly, the brightness can fluctuate with rotation and jets, and the orbit fit becomes sensitive to small forces that are hard to measure directly. And in that convergence, the first failures are human failures of prediction and tracking. A telescope points where the comet should be and finds empty sky. The software pipeline rejects good data because the comet's coma shape confuses the detection algorithm. An orbit solution that looked solid yesterday develops residuals that do not average out. A public tracker updates its forecast, and people interpret a routine refinement as a sudden course change. If you want to feel how this happens, imagine what orbit prediction really is. It is not prophecy. It is a best-fit explanation of positions measured against the stars. Each observation is a tiny pin pressed into a map. With enough pins, the path becomes clear. But when a comet is active, the pins themselves are harder to place because the point of light is not a crisp dot. It is a fuzzy coma, sometimes with asymmetric jets. The center of light can shift depending on exposure time, filter choice, atmospheric seeing, and how the coma is processed. In calm situations, those shifts average out. In tense situations, like the last few days before a geometry change, those shifts can mimic an orbital deviation. And because 3i Atlas is interstellar, it comes with a special complication. It crosses the sky in directions that can carry it toward denser star fields. A pre-covery study using test data discusses how the field becomes increasingly crowded as the apparent motion places it closer to the galactic plane, which is exactly the kind of observational environment where objects become harder to track cleanly. Crowded star fields are not just visually busy, they create false detections, blending and astrometric bias. They are where tracking systems begin to fail in the most mundane way: too many stars, not enough contrast, not enough signal. Now let's step into the 72 hours themselves, not as a list, but as a continuous flow of what changes as the encounter window closes. At 72 hours out, the orbit looks stable enough for planning. Observers schedule time on telescopes, amateur astronomers prepare, public websites publish predicted positions. For an object like 3i Atlas, even in late January 2026, people are still watching it as it heads outward. Space.com even highlighted a livestream event in mid-January, showing it on its way to interstellar space. That public attention is a gift and a hazard. It means more eyes and more data, but it also means more misunderstanding when the data shifts. At around 60 hours out, the geometry changes just enough that the comet's apparent speed against the background begins to feel jumpy. Not because it accelerates violently in space, but because the angle from Earth is changing and parallax, and perspective make the sky motion appear different night to night. In that window, measurement errors become correlated. You can still get good observations, but you have to be careful. Longer exposures smear the comet, shorter exposures reduce signal, and the coma can shift the centroid. The system under stress is not the comet. It is the compromise between exposure time and precision. At around 48 hours out, the orbit fit becomes sensitive to one question that keeps returning with active comets. Do we include non-gravitational acceleration terms? If you do not include them, you can still fit the data, but residuals may show structure. If you include them, the fit can improve, but you're adding parameters that can be underdetermined unless you have enough high-quality measurements. In a normal solar system comet, you can monitor for months and build a robust model. For an interstellar comet racing through and fading, you might only have a shorter arc of strong data at any given brightness level. That is where no one can explain it. Headlines are born, two different orbit solutions, both look plausible, and the public interprets the difference as mystery rather than as uncertainty. At around 36 hours out, the comet's own behavior can add texture. 3i Atlas has shown signs of evolving cometary activity, including rare sun-facing tail features and jets that wobble as the nucleus rotates. A rotating nucleus can make brightness fluctuate in a roughly periodic way. That is not just pretty, it can bias detection. When the object brightens more, telescopes pick it up. When it dims, fewer do. That changes the distribution of data points feeding orbit solutions, which can shift the fit slightly.
Rejected.
And when the fit shifts slightly, a public tracker might show a noticeable change in the predicted sky position a week ahead, which can look like a course change to people who expect orbits to be fixed. At around 24 hours out, the observing conditions matter more than you want them to. Weather eliminates a night of data. Twilight cuts into the window. The moon brightens the background sky. A crowded star field reduces contrast. And suddenly, the network of observations that would normally smooth out uncertainty becomes sparse. One missed night can be more significant for a fast-fading object than for a slow one. The system that fails here is simply coverage. At around 12 hours out, the orbit pipeline starts to lean on fewer fresh points. Predictions become more model-dependent. If the comet's outgassing changes, if a vent turns on or off, if dust production surges, if a fragment sheds, then the non-gravitational acceleration changes too. A tiny change is enough to show up as a growing residual over hours and days. This is especially true when you're aiming for high-precision pointing. A small offset can put the comet outside a narrow field of view. The telescope points and sees nothing. People call it lost. It isn't lost in space, it is lost in our model. And then the last few hours arrive and the story reaches the point where the title sounds most convincing: systems begin to fail. A detection algorithm trained on point sources rejects the comet because it is too fuzzy. A background star blends with the coma and shifts the measured position. A reduction pipeline applies an image subtraction that removes part of the comet's diffuse light. A human observer tired in the cold logs the wrong timestamp. A satellite ephemeris service caches an older orbit solution. A social media account posts a graphic of the predicted track that is now slightly outdated. And in that final window, the internet does what it always does: it turns routine uncertainty into a narrative. But if you look closely, the failures themselves tell you the truth. They are the failures you expect when you attempt something very hard, measuring a faint active interstellar comet with extreme precision as it moves quickly and fades into crowded sky. Now, because this video's title implies something darker, systems begin to fail in a way that sounds like infrastructure. It's worth being very clear and very calm.
Is that the outer ring, do you think?
3I
It
Atlas
must be.
poses
The
no
colours
danger to
are
Earth.
incredible.
NASA explicitly states there is no danger and that it will come no closer than about 1.8 astronomical units. So if you ever see the countdown language attached to this object in a way that suggests impact that is not science, that is atmosphere. The real tension is epistemic, not existential. It is about what we can know, how fast we can refine it, and how fragile our certainty can be when an object is faint and active. So what can actually fail in a way that matters even without any danger? One thing that can fail is navigation of our observations. That sounds abstract, but it matters because interstellar objects are rare. Each one is a once-in-a-generation data opportunity. If we miss point telescopes during a critical window, we lose spectroscopy that could have told us the comet's composition. If we lose astrometry around a key gravitational encounter, we lose the chance to measure how Jupiter's gravity and outgassing together shaped the outbound path. If we miss the window where a rare tail structure appears, we lose evidence about how dust and gas behave in foreign comets. Another thing that can fail is public understanding. This failure is quieter, but it spreads faster. When people think an orbit update is a course change, they begin to distrust astronomy, when the update later reverses. When people treat non-gravitational acceleration as unexplainable, they miss the actual beauty of comet physics. When people interpret Interstellar as controlled, they slip into stories that ignore the simplest forces in space: sunlight, sublimation, momentum, conservation. And a third thing that can fail is our assumptions about how interstellar comets behave. 3I Atlas is a sample of chemistry and structure formed around another star. It may carry different volatile ratios, different porosity, different dust properties than the comets we grew up studying. The wobbling jets and unusual tail geometry reported in observations are not proof of anything artificial. They are clues that interstellar comets can be dynamic structured and occasionally surprising in ways that our solar system comets already taught us, but now in a new context. And if you want one simple, steady principle to hold through this entire story, it is this: an orbit is not a rail. It is an evolving best estimate, especially when the object is active. Gravity provides the main shape, but outgassing can add small accelerations. In many cases, those accelerations can be modelled. In some cases, they can be measured only indirectly through residuals. And in the final 72 hours around a critical geometry change, those residuals become the loudest. Now let's talk about Jupiter, because it is the unspoken heart of this countdown. Jupiter is not a wall the comet will hit. It is a gravitational sculptor the comet will pass by. The predicted close approach in mid-March 2026 is about 0.358 astronomical units. That distance is huge compared to Jupiter's size, but Jupiter's mass is enormous, and its gravitational influence extends far. For bound objects, Jupiter encounters can completely reshape orbits, capture comets, or fling them outward. For an interstellar object already unbound, Jupiter cannot easily capture it into a permanent orbit, because the object's energy relative to the Sun is too high. But Jupiter can still bend its path, changing its direction slightly, and that bend can be measured if our tracking is good enough. That is why the last 72 hours matter. If you want to measure the gravitational deflection accurately, you need precise pre-encounter and post-encounter astrometry. If non-gravitational acceleration is significant, you need to disentangle the small push from outgassing from the small bend from Jupiter. That is an unusually elegant problem separating two different gentle forces acting at the same time, using nothing but distant measurements of a moving point of light. And if you manage it, you get something valuable. You get an improved estimate of the comet's mass and activity because a given recoil force produces a different acceleration depending on how massive the nucleus is. You get insight into jet behavior and how it changes with distance. You get a better outbound trajectory, which helps trace its incoming direction and perhaps narrow down the region of the sky it came from. You get a clearer picture of how common active interstellar comets might be. You also get a lesson in how astronomy really works, not as a story of certainty, but as a story of tightening uncertainty under pressure. Now, there is one more detail worth holding gently because it makes the phrase "systems begin to fail" feel almost poetic rather than alarming. 3I Atlas is leaving. It is already on its way out. NASA emphasizes that it will leave our solar system at the same speed it came in a one-time passage. Space.com framed January's livestream as a kind of farewell, watching it head for interstellar space. That means the countdown is not to danger but to absence. With every passing week it fades, recedes, and becomes harder to observe. The most important system failure is simply that our instruments have limits, and the universe does not pause for us. So what should you take from this in a way that lands softly even with a dramatic title? 3I Atlas is a rare interstellar visitor. It has already safely passed Earth at a great distance. It shows cometary activity including jets and unusual tail features that can produce tiny non-gravitational accelerations, small pushes that complicate orbit fitting, and as it approaches a key geometry moment like a Jupiter flyby in March 2026, the last 72 hours become a stress test of our measurement ecosystem. Crowded starfields, fading brightness, shifting viewing angles, and the delicate task of separating gravity from outgassing in the data. The comet does not need to steer for its predicted track to shift. It only needs sunlight and a few vents. And that is the calm ending that turns the countdown into something almost restful. 72 hours is not a threat. It is a window, a narrow window where a rare visitor is still bright enough, still measurable enough, still close enough by astronomical standards for us to learn something that will not be repeated soon. The systems that fail first are the systems that demand perfection. The sky rarely gives it. But if we keep measuring night after night, the failures turn into corrections, the corrections turn into clarity, and the drama dissolves into the quiet truth of astronomy. The universe is not trying to confuse us. It is simply moving, and we are trying to keep up.